Hello, this is AJ1, and this is our priority queue project presentation. First off, we're going to go over our implementation and talk about the parts that we're the most proud of. So first, we have the unsorted array min-pq, and we're really most proud of the simplicity of implementing the extrinsic min-pq interface using an array list. And because an array list is very easy to understand, the code itself is also very easy to write and understand.
For the hit min PQ, we're most proud of the idea that all the methods are implemented by calling the underlying priority queue class. So it makes the implementation so simple and also so effective.
And for the optimized heap min PQ, we really like the idea that we have this enhanced heap priority queue, which is supported by a hash map, and that's going to associate each item with its heap index, which is going to speed up both the contains and change priority methods. Moving into our asymptotic analysis, where we're going to run with the assumptions that were given to us in ED. We're going to start off with the remove min method, and for the double map min PQ, we theorized a worst case runtime of theta of log n. We came to this conclusion because the first key of tree map is going to take log n time, and the dot get of tree map is also going to get log n time, and the item to priority dot remove is going to take constant time with the assumptions. So overall, this would end up with a theta of log n worst case runtime. For the unsorted array min PQ implementation, we theorize a worst case runtime of theta of n. This is because this is just using sequential search to find the node with the minimum priority. So it's just going to loop through every item in the array, which will give us a worst case runtime of theta of n. And then for the heap min PQ, we theorize a worst case runtime of theta of log n. And this is because it's using Java's priority queue poll method, which takes theta of log n runtime, and then it's going to convert the priority node object to its contained item, which is a constant operation. So that just leaves an overall worst case runtime of theta of log n.
For the optimized min PQ, the worst case overall runtime is theta of log n. This is because with the assumption of for the hash map, the worst case overall runtime would be theta of log n, in which it has to sync the new item to the bottom of the heap. Next slide for the double map min PQ. With the assumption of the hash map, we also have constant time for all the methods here. But in worst case, it would take theta of log n for tree maps, get, remove, and add methods. For the unsorted array min PQ, we have theta of n time. This first has to search the item in the array list, then change priority for the item. So in the worst case, this needs to be all n items, which results in a linear runtime.
Okay, so for change priority of the heap min PQ, we theorize that this would have a theta of n runtime, and this is because the method first runs a theta of n exception check by checking if the PQ contains the given item, and then it removes that item from the priority queue from the Java's default priority queue remove method, which is another theta of n operation. And finally, the method adds a new priority node with the newly adjusted priority value into the priority queue, which would take theta of log n. So out of these three runtimes, theta of n is going to determine our runtime, and this makes the overall worst case runtime because of this, the overall worst case runtime is theta of n. Now, for the optimized heap min PQ, we thought that this would be log n because this method also runs an exception check, but this runs in constant time due to our hash map. And after that, this method runs a bunch of constant time operations to identify the item and change its priority, which are also constant time. And finally, it syncs and swims the adjusted priority node to the right spot. So this syncing or swimming will give us a overall runtime of theta of log n. Okay, so we're also going to talk about the impact of the tree bucket optimization. So we thought that the tree bucket optimization will not affect the asymptotic runtime, and that is because normally the runtime for accessing an element in a hash table is O of 1 amortized, which means that although the separate chaining does require us to iterate through a linked list, the length of that linked list is very small compared to n, which is the total number of items in our hash table. So when the linked list is converted to an LRB tree, it is true that the work required now is logarithmic instead of linear with respect to the size of the bucket. But since we're already assuming that due to resizing, the size of the bucket is going to very small compared to the total size of the hash table, the asymptotic runtime is still going to be O of 1.
Okay, and getting into some of the affordances of the intrinsic min PQ for content moderation. One of the first ones that we thought of was that medium toxicity comments are much more likely to get a pass since the comments are ordered from most to least toxic, which relates to the principle 2 about pervasive uptake and how the technology is actually adopted and used. It would be reasonable to assume that after seeing all the worst comments that some comments that are still pretty toxic get approved since they don't seem all that bad in comparison to the shock factor that's received from reading the worst ones first. Leaving these toxic comments on the website could drive people away from using the website because of the toxic environment and maybe feeling unsafe on the website, which relates to principle 1 and human values. In the actual website, this would lead to some toxic comments that maybe should have been removed remaining on the website. And this would not only dissatisfy users and disrupt their values, but it could possibly lead to a snowball effect of comments beginning to always be increasingly toxic because of the presence of other toxic comments. If you've ever heard the broken window theory, kind of like that, if there's toxic comments on the website, it will lead to more toxic comments being on it.
Okay, so for our second affordance, this is going to be about addressing the comments that need to be dealt with first. So the principles involved principles involved here are human values and stakeholders. So because the comments that were detected to be the worst and most of the destructive will be looked at first in the moderation process, this is going to have a positive effect on the website and overall user morale. And this is going to be a benefit to direct stakeholders in the company because potential business deals and advertisements will be hurt by the presence of toxic activity on the website. And users are also going to leave if they feel like the website is not a safe space. So as we see here, indirect stakeholders such as users and advertising companies would be the indirect stakeholders. And because of this, effectively handling the most toxic comments will prevent this from happening. And this does assume that the algorithm will be accurate in rating toxicity, which, as we're about to find out, is not going to be the case.
Okay, so for affordance 3, the limitation of the machine learning algorithm, using the machine learning algorithm would not always be accurate in assessing the toxicity of the comments. This is because it will filter out context. So when looking at what was said, the algorithm won't always be able to accurately judge the toxicity of it. When the moderator goes through the comments, they are likely to be influenced by the fact that comments are sorted from most toxic to least toxic, and begin to just judge the algorithm and not truly pay attention to certain algorithm, to certain comments. They are allowing onto the site. It could also lead to comments that didn't need to be filtered out, but getting filtered out because of lack of context and inability to judge tone. So this relates to principle 1 and 3 because the users of our website will value having comfort in using our website, and the convenience of knowing the things that need to be removed will be and the things that don't need to be removed. The direct stakeholders in the website will be affected as well because having a website with reputation of not running well will need to a decrease in user activity. Okay, so now we are in the critique and connect part. So this article is a reminder of over moderation is not necessarily good and definitely takes away the user's experience. Over moderation can lead to a lack of engagement in the comments themselves. leading us to ask whether over moderation is a benefit or harm for some things. For example, in the New York Times article where they brag about the success of their moderation, there's a severe lack of engagement with only 3 comments on an article from this big of a publisher. So this can be perceived as censorship by some users.
Yeah, and kind of on that topic of censorship, in our implementation, the monitors have legitimate censorship power in controversial things or cases of debate, maybe political, who knows. They have the ability to remove things that maybe they don't agree with and attribute it to them saying it's toxic or whatever. And so that's something that we do have to take into consideration, is the power that moderators have in deciding what people see and what people don't, and making sure that the right people are always appointed as moderators to ensure that censorship or unnecessary censorship, they're just opinionated censorship, doesn't happen.
All right. Yeah. So for our third point, it's actually going to be that we're going to tie it back to our extrinsic min PQ, and it's that the extrinsic min PQ relies on the success of the algorithm. So what we mean by that is that, as we talked about before, the extrinsic min PQ has a bunch of affordances that will have very real consequences on how the moderator and in turn the users behave on the website. But the extrinsic min PQ's purpose of delivering the most toxic comments first and then the least toxic comments later is only meaningful if the machine learning algorithm is successful at doing its job of accurately assessing how toxic the comments really are. And yeah, from what we learned in our articles so far, it's pretty unreasonable to assume perfection for a machine learning algorithm because of its inability to pick up on things like context rather than notice words that just might be considered bad. And yeah, that wraps up our presentation. Thank you for listening.
Thank you.